I will start off with presenting the first topic on the importance of minimizing cross-contamination steam sterilization. My name is Gary Bassi, and I'm the Director of Medical Device Reprocessing and Support Services at Mount Sinai Hospital in Toronto, Canada. I can disclose that I have no relevant financial relationships with any ineligible company, i.e. commercial interest. So our learning objectives for today's session is going to be examining the day-to-day challenges of steam sterilization and taking a look at some novel solutions, processes, and best practices in the industry. So let's talk about steam. The beauty of steam. So the beauty of steam lies in its simplicity. Physicists have yet to find a more efficient agent for energy transfer, which makes steam the ideal medium for sterilization. So we will now try to explain how this happens and why it's such a powerful agent for energy transfer. Water at any temperature will slowly but surely evaporate and become a gas. This, of course, is a natural process that happens because of the movement of the water molecules. But when water is heated and reaches 100 degrees Celsius, this process intensifies and the water evaporates at a much higher rate than before, not only on the surface, but also within the water. The vapor is visible as bubbles that rise from the inside the water to the surface and escape into the air. And this vapor is called steam. What actually happens is that the water expands in volume by 1,600 times when it changes into steam. Steam equals vapor, which is invisible. So if you look at this picture here of the kettle, the clouds are steam condensate. The steam turns back into water as it hits the cooler air, forming water droplets. So often we would refer to this as the steam coming out of the kettle there, but actually what you see, what's visible, is actually the condensate that's turned back into water, which is why you can see it. It's a bubble of water droplets there. Steam contains enough heat energy that it can destroy bacteria. As I mentioned earlier, it's a very powerful sterilant. And when steam contacts a cooler surface, it transfers that energy that it contains to that surface. And that energy is what destroys any bacteria present. So it's important we remember it's not the steam that destroys the bacteria, it's the energy that the steam contains and the energy itself that destroys the bacteria. This is why steam is so effective, cheap, and safe to use in medical device reprocessing. Easily generated, safe, and effective. Saturated steam is what we aim to produce, as it contains only a very small percentage of water, usually less than 5%. So if we take a look at this slide here now and discuss some of the challenges of steam sterilization. Steam, as we know, often travels distances through piping before it actually enters the sterilizer or the autoclave chamber and eventually makes contact with the contaminated load that we're trying to sterilize. Now, during this travel path, many things can influence the quality of steam on its mission to reach the load and kill the bacteria. So as you can see on the diagram here, steam traveling through a pipe, there's condensates that is being discharged through the drip legs. And we're going to talk a little bit about what some of these challenges look like. So a number of challenges that you may experience when using steam sterilization. First one being wet steam. Wet steam is basically steam at saturation temperature containing more than 5% water. Wet steam lowers the heat transfer efficiency of steam, which will result in inefficient sterilization procedure. Wet steam causes several major problems. So, as we discussed earlier, as steam travels through the piping, it can condense. Piping that's not properly insulated can cause additional problems to that. And steam traps are fitted on the system and help by trapping steam condensate and returning it to the boiler or drain. So again, piping needs to be insulated. Steam traps need to be working effectively to allow a good quality of steam to enter into the autoclave. Steam traps that are not routinely maintained can stop functioning the way they should and become trapped with dirt, making them less effective at removing the condensate. And wet steam itself inside an autoclave will clog the pores of the packages, such as the sterilization wrap that we use, preventing steam from penetrating the package and actually contacting the surface of the device that we're trying to sterilize. The sterilization package itself can also absorb the moisture, which will then equal a wet load. And we know that a wet load is something we don't want because moisture itself is conducive to bacterial growth. So those of you who may be wondering why wet steam is a problem, but why? These are the reasons why. And to further add to the list of problems why wet steam is not a good type of steam to use, if you're sterilizing stainless steel surgical instruments, wet steam will further exaggerate the problem of corrosion and spotting. A lot of moisture on your instruments sitting there doing nothing could end up causing corrosion and water spots, so that when packages are opened in the OR, you'll have additional issues that the OR will report in terms of corrosion that's appeared now on an instrument that wasn't there before you sterilized it. So always good to look out for these things. If you're seeing an increased rate of incidents being reported for water spots or corrosion occurring that wasn't there before sterilization, it might be a good time to check the quality of steam. So one of the things I want to point out on this slide is that, again, if you look at how steam is generated after boiling water on this graph here, you see that steam itself contains that energy that we talked about, specific entropy, and the temperature on the y-axis. So as the temperature increases, the entropy is also increasing. But as you get to a certain point, which is where you want saturated steam, which is why we use 135 degrees Celsius for pre-vac sterilization cycles, that is the steam that has the most amount of ability to be able to destroy the bacteria in the shortest cycle time. And we'll talk a little bit about that later on here. One of the other important points to point out here is when you're commissioning steam in redevelopment projects. So the guidelines that are contained in the standards EN 285 and HTM 2031, also ISO 17665-22009, when you're commissioning new autoclaves, before you turn your autoclaves on, it's very important you commission your steam. And that involves testing it for its dryness, non-condensable gases, and the superheat, to check if it's superheated steam and what those values look like. Those values are correlated back to the standards that I mentioned. And normally the steam is sampled and condensed in a chemically inert condenser, and the resulting condensate samples are tested. So this slide talks particularly about when we actually commissioned our sterilizers here at the hospital. We tested for these items. The lab results were returned to us almost 3 weeks later, and the results and the associated test limits recommended by the standards are shown here. This slide tells you how dry the steam should be. The standards state that it should be greater than or equal to 95%. So that we ran 3 tests and all of them were greater than 95%. The non-condensable gases should be less than 3.5%, less than or equal to, and all of our results indicated very, very, very low non-condensable gas presence. Superheated steam should be less than or equal to 25 degrees Celsius here, and we had very low values showing that we didn't have presence of superheated steam. Another test that's very important during the commissioning of steam, other than just checking for its dryness and non-condensable gases and its temperature in terms of superheated nature, is the purity of the steam, the mineral content of your steam. This itself can also be a problem in many ways, which I'll explain. When we test for steam purity, again, we correlate that back to the standards and what the standards state in terms of what the percentage or concentration of minerals should be in the steam. So we have here the lowest detectable limits, the test results that we conducted on our steam and how it correlates back to the standards EN 285 and the ISO standards. So as you can see here, we were lower for calcium carbonate, chlorides, within the range for pH, conductivity, alkalinity, acidity, and the dissolved metals. So we were lower than or equal to in all aspects here from a standards perspective. This is important, what I just showed you there in terms of purity, because minerals themselves inside steam can present a problem because they can deposit onto the instruments, specifically causing staining and other types of contamination that may come through. So it's very important you have good quality steam that you're running in your sterilizers. And we touched a little bit on superheated steam. Now, superheated steam, of course, we know is not good. And the reason is that it may have a higher temperature, but its ability to destroy bacteria within the same time exposure is reduced. If the speed in the steam lines is too high, i.e. the steam being delivered to the autoclave chamber is coming in at too much of a fast speed, you can get superheated steam, meaning your autoclave will end up functioning like a dry heat sterilizer. Dry heat sterilization takes much longer. 180 degrees Celsius at 30 minutes will give you the same kill that 135 degrees Celsius at 4 minutes will give you. And that's because, as I showed you on the previous slide, the energy that superheated steam holds and the content of the steam itself in terms of the moisture. Why this is bad is particularly is not only does it take a longer cycle, and if you've got your sterilization parameters set for 135 degrees Celsius in 4 minutes, and you're using superheated steam, then you've got the wrong exposure time for the wrong type of steam that you're using. So you're not using the right type of steam for that cycle, and as a result, scorching is something that we've seen in the industry that can occur on wrapped packages. You can see it on towels and instruments where you get almost like a burning effect. Another thing that's important is steam pressure and dead legs when you're designing a steam sterilization department. Inadequate steam pressure can cause many problems, and particularly it can burn out the condensate pumps. Most of the time you'll see sterilization manufacturers recommend 60 psi steam delivery to the autoclaves. And what can happen is if you've got steam being supplied to other systems in your reprocessing centers, such as your cart washers that may use steam, or any other washers or any other machinery that's dependent on steam, and if it's all coming from the same line, the equipment that's furthest away from the branch of steam delivery could end up getting reduced pressures. And ultimately what could happen is the condensate pumps, which are responsible for removing the condensate, problems can arise there. So you want to make sure that you have the right amount of steam. Also, in addition to this, is that the water pressure itself, condensate pumps use water to be able to remove the condensate, and if there's not enough water pressure, the condensate pump itself could burn out because it's running dry, and it is a very expensive part to replace, often in the range of $9,000 to $10,000. And again, like I mentioned, the sterilization cycle valves could present a problem. If the steam pressure is too high, then those valves that open and close could also end up having issues where the pressure is too high, preventing the valve from closing. And if the valve is left open, then you could end up getting alarms for too high temperature as steam continues to enter. And then dead legs is important when designing a steam system. Dead legs should be avoided as per the standards. A dead leg is a section of pipe that leads nowhere and does not form part of a constant circulation system. In a steam line, condensate can form in a dead leg and become stagnant. And branch steam line should exist from the top of the main lines to reduce condensate carryover. The accumulation of condensate during the periods when the sterilizer is not in operation should be avoided, particularly in any part of the pipework and fittings between the takeoff from the manifold and the sterilization chamber. This can be achieved by the correct declination of each portion of pipework, so the angle at which that pipe sits, and by adequate trapping throughout steam distribution system. Next slide, we're going to talk about feed water. So the feed water that the steam is generated from. The modern compact high-rated boilers and steam generators are particularly sensitive to the quality of feed water and much more likely to prime the boilers of traditional design. Priming or foaming, which results in carryover of boiler water, can result from being undersizing the boilers. The boiler should be designed for, at minimum, the required peak demand for all steam equipment running at the same time, i.e. including your washers, cart washers, etc., and treating the feed water incorrectly. So treating the feed water incorrectly would be a big problem because you're going to have a lot of additives added to your steam and other issues I talked about, minerals entering your steam. So setting the boiler water level too high, forcing a boiler that needs internal cleaning, violent boiler under fluctuating load conditions, and a high level of total dissolved solids. Superheated steam is unsuitable, as we've already discussed, and for many reasons, and we've talked about how it can be generated, and how it's not a liked thing to have superheated steam in reprocessing departments. So a lot of this information is taken from the CSA standards. So there's guidance there for those who are designing your departments, and guidance is there for construction contractors in terms of dead legs and feed water. Another challenge steam sterilization is your staining of your chambers. So it's important you upkeep a routine cleaning maintenance of your sterilization chambers, making sure that the substances that are built up are removed, and this will obviously improve drying and heat transfer within the chamber walls. It will reduce the contamination that can, from condensation that could leak onto your packs, causing you to reject those packs. And cleaning it more frequently would be an easier routine for the operator, cleaning it than cleaning it after an extended period of time where there's so much staining that is built up. Also note on the picture here, you have your door gasket that needs to be checked on a constant basis, especially if the gaskets are being filled with steam, then steam could be leaking out, but the gasket itself also needs to be cleaned and wiped and inspected. And then let's not forget how important parameters are to check when you're dealing with steam sterilization. So when we talk about parameters, we're really talking about monitoring the pressure, the temperature, at the exposure time, 135 degrees Celsius, 4-minute cycle, 10-minute cycle, whatever cycle your facility may be running, making sure that at the end of the cycle is completed. When you're running a leak test on some sterilizers that require leak tests, making sure that your values are within the leak test ranges, the leak rate ranges specified by the sterilizer operator. Some sterilizers require a Bowie-Dick test, making sure that we've run a Bowie-Dick test. Indicators in the sterilization load have passed, or the indicator on the biological. The biological itself has passed. The quarantine period for the sterilization cycle where the medical device have exited the sterilizer but now need to cool before we can touch them. And then, temperature guns are often used for that quarantine period, because if packages are hot and we're not using sterile gloves to handle them, then we could impose further contamination. So some facilities use temperature guns to measure the temperature of the package before handling them to know that it's cool enough to handle. And this temperature gun that I've shown here is a thermal temperature gun, which allows you to penetrate a couple of inches into the package and not just the surface temperature. So parameters are very important to monitor for steam sterilization, and this is a few parameters I've listed here. Cleaning your sterilization cart similar to the chamber. Again, another challenge that could cause your packs to be contaminated by transferring the contaminants from the cart to the packages. So upkeeping them and making sure they're nice and clean. Some of them can be run through the cart washer. Some of them can be cleaned the same way as your chambers. Load configurations. Load configurations are very important to get optimum steam sterilization. Particularly, I like to think of it as a pyramid structure where we put the heaviest mass at the bottom and the lightest mass at the top. So as you can see from the first picture in the middle there, you've got containers sitting over wrapped items. This is usually not a good situation where steam will condense at the bottom of the container and drip onto the packages. So we like to build our configurations where we have all metal containers at the bottom, wrapped items above, and then peel pouches. As I mentioned, similar to a pyramid structure where you have the heaviest mass at the bottom and lightest mass at the top. And now let's talk about non-condensable gases. So we've talked about parameters and all the other things that we need to measure and constantly monitor, but how are we measuring non-condensable gases in steam sterilization? The literature shows that every steam sterilization cycle is a unique event and that the steam composition is different in every process. How can we achieve parametric release protocols if we are not checking all the parameters as per the ISO standards? Essential parameters we know are temperature, pressure, and measuring non-condensable gases. Pressure and temperature, we already discussed how we measure that. There's gauges on the sterilizer. The printout shows you what the temperature and pressure was achieved. But what about non-condensable gases? The Bowie-Dick test that we do is often referred to as a steam penetration test. But it's actually a postulated relative measurement for non-condensable gases. Why, and the other question we should ask ourselves is, why is only the first empty load measured with the Bowie-Dick test? What if there is presence of non-condensable gases during a cycle in the other consecutive loads that we run? Should we not be monitoring every load considering the definition that each sterilization cycle is a unique event? And knowing that the Bowie-Dick test is a mechanical test to perform at the beginning of the day to test the removal of air and steam penetration, empty chamber without a load. The test, it was a big step forward for sterilization monitoring, but it's almost over 50 years old. And at that time, there were very few channeled instruments and lumen instruments that we see today, and the packaging was mainly performed with linen. And steam penetration mechanism in textiles differs strongly from steam penetration in lumen devices. So I think we should ask ourselves, is the Bowie-Dick really representative of the everyday load we see today with lumen devices? Here on the right, you can see a picture of a typical Bowie-Dick test where we look for this faded color to see if there's any air in the chamber, but it doesn't really tell us if it doesn't quantify what's in the chamber. Is it non-condensable gases, or what is actually in the chamber? It tells us there's something there. Current devices that are on the market here, this slide will show you some of these novel devices that are already existing on the market to do electronic Bowie-Dick tests. And some of these are, some institutions use these, but again, none of these devices are able to quantify the number of non-condensable gases in your chamber. So if we take a look at some novel solutions that have been developed, Steelco, a sterilization company, has developed an infrared sensor to provide quality assurance of steam penetration. And the Catharina Hospital in the Netherlands has developed a unique parametric release protocol based on all the parameters that need to be measured as per the standards by using a device that's been developed to measure non-condensable gases in each load. So let's take a closer look at some of these solutions. So this device allows you to do every load monitoring with a 4D infrared sensor. Let's look at how different this is compared to our regular Bowie-Dick test. Note the differences, monitoring versus measuring. This provides a numeric indication of steam saturation to define a pass or a pass with warning or a fail. A pass with a warning alerts users that steam sterilization may need maintenance, but the sterilization conditions currently comply with the specifications and the standards. So what's happening here is they've designed a device which allows steam to enter the lumen and cut the infrared light off, which is then measured. And this gives you a value to give you confidence that steam penetration has been achieved. So if we look at this video, this shows you how the 4D sensor works that they have developed. 70 centimeter narrow lumen with 4 millimeter constant radius and open distal end. Steam enters. It cuts off the infrared light at the proximal end of the lumen, and the steam density is now measured, which then allows you to see if you have effective steam penetration. So it measures steam saturation, the only parameter that can guarantee that sufficient steam is present in the sterilizer chamber and load, and that there's no excessive residues of non-condensable gases. The measurement takes place at the closed end of a long, narrow lumen, as we just seen, to simulate a worst-case scenario of the most challenging hollow surgical instruments. This is different to our standard Bowie-Dick test paper, because this actually represents a real scenario, real situation for the real type of devices that we sterilize. The emitted infrared radiation is filtered by the steam according to its concentration value. So it measures the steam saturation, also known as the density of the steam, the only parameter that can guarantee that sufficient steam is present in the sterilizer chamber, and that the load and that there are no excessive residues of non-condensable gases. The measurement takes place at the end of the lumen, as we've seen. And basically, the concept is that when you imagine yourself standing behind a window in direct sunlight, the UV light from the sun tans or even burns your skin. But when you stand in front of the sunshine without the glass, it can burn your skin. But when you stand behind the glass itself, the glass, it filters out those damaging rays. And similarly here, the sensor is the same type of concept. The steam, the light can penetrate normal air, but it can't travel through steam. So steam cuts off the percentage of light that's actually being transmitted through it. So that reading is then measured. So the steam filters the infrared light, just like the glass filters the UV light. The greater the absorption of the infrared light by steam, the higher the saturation of steam. So based on that, steam presence and steam penetration are proven, monitored, and registered in real time during the sterilization cycles and every single second, together with other relevant cycle parameters. So this is how it looks inside the chamber. It's fitted on the left-hand side of the chamber, and the reading is taken. There's software that will able to compute the values. So and here's another non-condensable gas sensor that we talked about, that Katharina Hospital is using and have developed a parametric release protocol based on this. So they've installed one of these sensors, which is different to the 4D sensor that we just talked about. This sensor has been installed on the validation ports on each sterilizer. Within 30 minutes per sterilizer, the non-condensable systems were installed. So it's a very quick installation. And the sensors come with generic calibration. They come with a software, and they've proven to be very reliable for them. The sensors are connected via USB connections to one of the computers at the unloading side of the sterilizer, and the computers are fed via one UPS power supply, and they're connected to a network printer. The sensors are completely independent from the sterilizer, and the software that they use recognizes when a process is started on a sterilizer. The sensors measure, the software will be able to tabulate the temperature, pressure, and the amount of non-condensable gases during the sterilization cycle, in every single cycle. And within a minute after the process, it's plotted with the software and can be printed out. The file of the process is also digitally stored, and the staff check the printout immediately after the process and can then, based on that, can immediately release the load. There's no incubation times or interpretation of chemical indicators needed. And because the non-condensable sensor runs 24/7, it appears to be very helpful for troubleshooting issues in the sterilization cycle. They have found it to be interesting and have noticed some interesting events on their sterilizers which were not noticed before. The NCG sensor allows them to be able to correlate the three readings together, temperature, pressure, and non-condensable gases, and ensure that they meet the standards for every load and process, going back on the definition that every cycle is a unique process. They've stopped the Catharina Hospital particularly have now stopped performing the daily Bowie-Dick test, also known as the daily steam penetration test, and have started using this non-condensable gas sensor only. And again, that has resulted in them reducing their consumable costs because there's no consumable pack that needs to be purchased anymore, i.e. the Bowie-Dick test. They've stopped their yearly validation, only performed a verification measurement when they've had a serious change in the sterilizers. And because the system is automated and does not ask for human handling, it saves them time, it reduces human mistakes. There's no need to remember to put a pack in. It's just monitored and done on every single cycle that's ran on the sterilizer. It's real-time results, and the staff are very happy and like to use this sensor because particularly it's evidence-based and there's no waste of any material, less use of water and energy for running empty cycles with a Bowie-Dick. So they've done some business case in terms of how it puts money back in their pocket. What does the sensor look like? And this is how the sensor works. So the previous picture I showed you showed the sensor connected to the validation port. At the top of the sensor is a unique cooling device. And similar to the 4D sensor, is based on the lumen to be representative of a challenge of the load that we sterilize. So it's designed by Solid 2. And here's how it works. During a sterilization process, steam enters the measuring tube. The top of the tube is cooled to a lower fixed set temperature. So where you see T1 on this picture here, that takes the temperature at the top of the tube. And the typical temperature being 40 degrees Celsius. As a result, the steam will condensate and be discharged from the measuring tube along the wall of the tube. So when you have this steam now at 135 degrees Celsius entering this tube, it hits that cooling device, automatically condensates because the cooling device is at a much lower temperature of 40 degrees Celsius, and it runs down the side of the tube where you can see on the annotation there where it says water film. The non-condensing gases will remain at the top of the tube, and these will then form an insulation layer. The more non-condensable gases there are, the larger the insulating layer. So if you compare the picture on the left and the right, you can see that the non-condensable gases, the layer is larger on the right than it is on the left. Over the measuring block, between the measuring tube and the cooler, the temperature difference is measured by subtracting T1 from T2. Difference in that temperature reading is known as the DT sink. The DT stands for the delta, temperature, and sink for Coldwell. The larger the insulating layer of non-condensable gases, the smaller that value becomes. It's therefore a measure of the amount of non-condensable gases in the measuring tube and thus also of the sterilization chamber. So how does that value tell us that it's a larger layer of insulating gases in non-condensable gases? So if you've got steam coming in at 135 degrees Celsius with a very small number of non-condensable gases present, then we know that the steam, when it hits T2, is going to be very close to 135 degrees Celsius temperature or higher. And then when it hits T1, we know that it's going to drop very, very quickly, and that delta is calculated. Whereas on the picture on the right, where you've got a larger insulated layer, when the steam hits T2, it's going to be at a very low temperature, less than the temperature that was on the picture on the left. And then when it hits T1, it's going to be at much lower, closer to 40 degrees Celsius. Therefore, because the two values are going to be low, the DT sink is also going to be low. Whereas the picture on the left, the difference in the values is going to be high because the temperature of the steam at T2 is much higher. Therefore, this sensor is based on the fact that that difference in steam temperature between T1 and T2, the lower that value is, meaning that there's a higher number of non-condensable gases preventing T2 to have a higher temperature, which would have given you a larger DT sink value. So it's compliant with the standards, and the minimum value as specified in the standards can be set in the software. It can be used standalone, connected to the sterilizer controller, and remotely read out. It's the real parametric load release is evidence-based, no separate steam penetration test is required. Less frequent air leakage tests are needed, reduction of validation and monitoring activities, less handling for the staff in terms of putting packs in the sterilizer. and it's improved safety, improved quality, and can be a return of investment. Here's some examples of what the readouts look like from the software that the staff use at Katarina Hospital, particularly here. And there's values. It's a little bit small text to see, but there's values there that they correlate back to in terms of a pass and fail. And that's the end of the slide. So I'd like to thank everybody for attending this session today. Thank you, everybody, for listening in to our educational session today. And we're going to open up the Q&A panel to answer some questions that we've received. So one of the first questions we received is, how do you test the moisture in the steam? And do you need a third party to do this test? And typically, what companies are out there that test the moisture in the steam? So yes, the moisture, sorry, the question was, how do you test the moisture in the steam? Yes, the moisture is tested, and is tested as I explained in slide 8, as per EN 285, and it has to be greater than or equal to 95%. I don't know the specifics of exactly how they test the moisture in the steam, but there are third-party companies. I haven't been in a facility that they've done it in-house. Normally, it's tested by a third-party company. It's typical of pharmaceutical applications to have this type of testing done. And in Canada, we used a specific company that works with big pharmaceutical companies that have industrial sterilizers and healthcare facilities to test the dryness of their steam. So if you, I think, do some research on sterilization validation, steam dryness validation companies, you'll be able to bring up some results for your respective area. Next question we had is, what is the recommended cleaning times of the sterilizer chamber, i.e. how often? So this is a good question, and really it's representative of each and every manufacturer's sterilizer. So I would point you to the instructions for use for your respective sterilizer. Every manufacturer differs. One manufacturer may state that it needs to be done routinely on a weekly basis or bi-weekly basis. Other manufacturers may have varying instructions for their sterilizers. All right, so we have another question. Did you say we can put the sterilization carts through the cart washer to wash them? I did say that. Sterilization carts are typically stainless steel, and as are our surgical instruments. And if your cart washer is adequate in size to accommodate the manifold going through, it's a good way of descaling the sterilization manifold to remove any mineral deposits. Now, again, each and every manufacturer has its own instructions for use as to how to clean their equipment. I have in the past used a gel of some that was of some chemical nature to apply to the sterilization manifold, and then descaled the manifold itself through the cart washer, which worked out great. But again, I would defer to the instructions for use from the manufacturer. We have another question. Can you explain if the Bowie-Dick test can be put in each load? Good question. So the Bowie-Dick test is typically run on your sterilizer on the first, as a diagnostic test on an empty sterilizer. And normally the cycle on the sterilizer is 3.5 to 4 minutes. Now, one thing to note is that the Bowie-Dick test does not incorporate a dry time in the cycle. So therefore, placing it in each and every load, A, would not meet the manufacturer's recommendations of the Bowie-Dick instructions, and B, the dry times on each load may impact the results of the test. Therefore, the Bowie-Dick test is run on its own in an empty chamber. We have another question here. Are all sterilizers compatible with clean steam? So this is a good question. Most sterilizer manufacturers have the options when procuring their sterilizer if the facility intends to use clean steam generated by RO water or steam generated by filtered utility water. And it's a very good question and a good thing to know the answer up front before you make your decision in purchasing a sterilizer, because the fittings of the sterilizer for many sterilizer manufacturers, the fittings also have to be compatible with the steam. And often you would find an increase in cost if you intend to use clean steam, because those fittings, such as brass and copper fittings that they intend to use, may not be applicable in a clean steam environment. Whereas typically when using utility water to generate your steam, a sterilizer that may have copper or brass fittings. Another question we have here, chemical indicator tape. So is it necessary to use the autoclave tape on packages to wrap the entire package? And can the chemical indicator from the tape bleed onto the packages below? So I have seen that in my practice before. The chemical indicator tape that's commonly used, the indicator, the black lines that appear after a sterilization process, we have seen that bleed from the tape. And I believe that some manufacturers are trying to address the problem. And to answer the second part, do we have to use it to wrap the entire package? It depends on the standards in your area. Certainly the standards in Canada do allow you to use autoclave tape to seal your package as a closure tape, and a indicator tape on the outside of the package to indicate if it's gone through the sterilization process. It does not require you to use indicator tape to wrap the entire package. Or validated autoclave tape may be used that may not have an indicator, but the presence of an indicator tape somewhere on the package needs to be there. Another question we have is, how important is load configuration, and what about sets which are very dense, such as orthognathic implant sets? So load configuration is a very important element in terms of loading your sterilizers. And as I mentioned earlier in my presentation, we normally teach the staff to think of a pyramid with the most dense sets at the bottom of the bottom shelf of the sterilizer card, and the most lightest packages at the top. Now, you do have some sets in orthopedic facilities which are very dense, and orthognathic sets known to have a number of cassettes inside their tray have in the past created a problem, because it's difficult for, I guess, the moisture or the set to dry adequately. So what I can recommend in instances such as that is you need to monitor how your sterilizers behave with certain sets, and perhaps increase the dry time if it's concordant in the written instructions from the manufacturer of the tray, and increasing the dry time from what your common dry time is to perhaps 40 minutes dry time for sets that are difficult to dry. All right, and then we have our last question here. Is there a need to have a self-cleaning cycle on sterilizers? Good question, definitely an innovative question, something that could be thought of in the future for sterilizer manufacturers, to possibly drain and flush a sterilizer chamber after the cycle is completed. I don't know, is there a need? We do need to definitely clean the sterilizers, as mentioned earlier, and any automation is always, any automation that produces good results could always be looked at for each department to foster that innovation. And that concludes our questions and answers session. And I'd like to thank everybody for listening into the presentation and attending the question and answer session today. And stay tuned for the next educational session that we offer. Thank you again.